So this video is some selected problems from the second practice test. In which of the following compounds is the mass ratio of chromium to oxygen closest to 1.3 to 1? So when they say the word ratio, always think fraction. And so the fraction that they want is chromium divided by oxygen, 1.6 divided by 1. And so if you look at the possible choices, first you need to know the atomic masses, or the formula masses of chromium and oxygen. And if you look on the periodic table, here's chromium and here's oxygen. And then if you look at the answers, letter C has 1 to 1 ratio because there's 1 chromium and 1 oxygen. And so you take chromium on top, which is 52, divide it by 16. If you do that in your calculator, you get 3.25, and you can write that answer over 1 because any number written over the number 1 is that number. And chromium, of course, would be on the top because chromium's on the top here and oxygen would be on the bottom. It asks for a ratio of 1.6 to 1. This gives 3.25 to 1. Look at answer B. In answer B, they have chromium to 2 oxygens. So 52 to 16 times 2. This, when you do it on your calculator, is 52 divided by 32, which gives you approximately 1.6 to 1, which is the answer you're looking for. If you just want to make sure, go ahead and try the answer A. In answer A, they have chromium is 52, and then oxygen is 16, and there's 3 of them. And when you divide these, it's 52 divided by 48, which is 1.08 to 1. Hopefully that helps you answer question number 12. Let's go to question number 14. And in question number 14, what they want is for you to use something called Hess's law. And in Hess's law, what you do is look at a goal reaction that they give you, which is listed right down here, and you say, how can I use other of these reactions, manipulate them, either by multiplying them by a number, turning them around, dividing them by something, and then adding them together to get the overall enthalpy or energy of the reaction. And so start with the goal reaction and say, where is Na2O, or this reactant, in one of these reactions? You can notice that Na2O happens to be on the wrong side of the reaction compared to my goal reaction. And so let's take that reaction and let's flip it around. And if I reverse that reaction from what I'm given, I will have to reverse the sign of the enthalpy. The enthalpy given is Y, and I'll reverse it to be negative Y because I reversed the reaction. Take a look at the second item that I need. I need H2O, and I'll notice that H2O is right here in this reaction, and I need it on the left side of the reaction, so I'm going to flip that one around as well. And so I'm going to make that be the backwards of that reaction, and so I flip the sign of the enthalpy. It will now be negative X instead of positive X. Lastly, I need to find NaOH, and 2 of them. And you'll notice that NaOH is in this third reaction, but there's only 1 of them. So I'll take this reaction and multiply it by 2. So I write this reaction, and then I multiply it by 2, knowing that I'll distribute this number 2 into each one of these species right here. And that forces me to multiply the enthalpy by 2 as well. Now let's go ahead and add all the things on this side of the reaction together, and then add all the things on this side of the reaction together. And you'll notice when I write all of these things down and distribute the 2, and I write all of these things down and once again distribute the 2 to the NaOH, then I can cancel the species that are the same on both sides of the reaction. So you'll notice that I have 1/2 O2 here and 1/2 O2 here. If I put those together, they make 1 oxygen, and I have 1 oxygen right here. You'll also notice that I have a Na, 2 of them right here, and I have 2 NAs right here, and I have an H2 right here, and I have an H2 right here. Notice I have 1 of them because remember I distributed this 2 into here. The remaining items, H2O, Na2O, are my reactants, and 2A, NaOH, which are my products. Since I've proven that I can add these reactions this way by manipulating them and canceling species that are the same on both sides, I can now take these three enthalpies, add those together. So the enthalpy of the reaction is the negative Y plus the negative X plus the 2Z, and this turns out to be answer D right here. Let's take a look at number 17 next. In number 17 they say, if 87 grams of K2SO4 are dissolved in enough water to make 250 milliliters of solution, what are the concentrations of the potassium and the sulfate ions? So the first step is to take the 87 grams and convert it to moles. Once I have it converted to moles, then I will use the molarity triangle to find the concentration of K2SO4. So I'll take my moles and divide them by my liters. It tells me there are 250 milliliters, which is 0.25 liters. Divide those two and I get 2 molar solution of K2SO4. Now be careful, because the K2SO4 will dissociate to give you 2 K pluses, which is the K plus ion in this case, and SO4 2 minus ion. And it asks what is the concentration of each of these in the solution. So take your 2 molar and you'll have to multiply it by 2 because there's 2 K pluses. So you end up with 4 molar K plus and 2 molar SO4 minus, because there's one of these for every one K2SO4 that dissolves. This is answer E. Let's look at one more problem in this short cast. Let's look at number 19. It's suggested that SO2, which contributes to acid rain, could be removed from from a stream of waste gases by bubbling gas through 0.25 molar KOH, therefore producing K2SO3. What is the maximum amount of SO2 that could be removed by 1 liter of the KOH solution? And here's my balanced equation. So you should follow the steps of a stoichiometry problem. Step number 1, write the balanced chemical reaction. Step number 2, convert to moles. I'm given the molarity and I'm given a volume. And remember that the molarity triangle is moles are equal to molarity times liters. Molarity times liters. Once I have the moles, I'll notice I only have one item, so there's no limiting reactant. This is my limiting reactant. And so then I need to do the mole to mole ratio, which is for every 2 KOHs, there's 1 SO2. And then step number 4, convert to the asked for units, which is what is the maximum mass of SO2, so grams of SO2. And I get 64 grams by adding it up on the periodic table, which if you add up 1 sulfur and 2 oxygens, you end up with 1 sulfur and 2 oxygens. You end up with 64. This ends up being 8 grams, which is letter B. One last one. Let's take a look at a lab question. It says, correct procedures for titration include which of the following? Well, this is a lab technique type question, and you need to know what a titration is. And a titration uses something called a pipette or burette. And pipettes or burettes are devices that are used for accurate measure of particular concentrations of solutions. And so you want to keep the concentration of the solution inside the burette or the pipette exactly the same. And one of the things that you want to do is also accurately measure that amount of solution. One technique to do that is by draining that pipette or burette by touching the tip to the side of the container used for the titration. You want to do that because then any drops that form from the solution will go into the container that you're going to use. You also want to swirl the solution frequently during the titration so you have accurate mixing. The second one, which is not true, is to rinse the burette with distilled water just before filling it with the liquid to be titrated. You do not want to do this one because you will take and add or have some small drops of distilled water inside of the burette or pipette before you add that liquid or that solution that you want to know the accurate concentration of. And then you'll be diluting that solution by having a little bit of water inside of there before you do the titration or use the pipette to distribute your solution. So you want to make sure to actually rinse it with the solution that you're going to use first and then add your solution. So 1 and 3 are the correct answers.